For nearly half a century, a burning question has puzzled scientists. Why do solar flares, the most explosive events in our solar system, leave behind such mysterious spectral signatures? But here's where it gets controversial. A groundbreaking study from the University of St. Andrews suggests these flares might be far hotter than we ever imagined, challenging long-held assumptions about the sun's behavior. Solar flares. Those dazzling bursts of radiation tied to sunspots have captivated astronomers since their discovery during the 1859 Carrington event, the most powerful solar storm ever recorded. Yet, despite centuries of study, one enigma has persisted: the unusually broad spectral lines observed in extreme ultraviolet and X-ray light. These lines, like fingerprints of the sun's activity, hinted at processes we couldn't fully explain. Until now. And this is the part most people miss. While we've known the sun's composition since the 1868 eclipse, the extreme temperatures and energy dynamics within flares have remained elusive. Enter Dr. Alexander Russell and his team, who propose a radical idea. Ions in the sun's plasma can heat up to a staggering 60 million Kelvin, while electrons stay relatively cooler. This defies the traditional belief that ions and electrons share the same temperature, a cornerstone of solar physics for decades. The key lies in a process called magnetic reconnection, which heats ions 6.5 times more than electrons, a phenomenon observed in near-Earth space and solar wind, but never directly linked to solar flares. This appears to be a universal law, Dr. Russell explains, and it opens the door to understanding why flare spectral lines are so broad. Here's the bold part. If this theory holds, it could rewrite our understanding of solar flares. Previously, scientists attributed the broad spectral lines to turbulence, but with super hot ions in the mix, those calculations may need a major revision. The team's findings, published in the astrophysical journal Letters, suggest that turbulence plays a smaller role than thought, with energy distributions shifting dramatically during flares. So what's next? The researchers call for advanced thermal mapping of the sun, a task perfectly suited for NASA's upcoming MUSE and EUVST missions. These tools could finally provide the data needed to confirm or challenge this paradigm shift. But here's the question for you. If solar flares are indeed hotter and more complex than we realized, what does this mean for our predictions of space weather and its impact on Earth? Could this discovery lead to better protection for our technology and astronauts? Let us know your thoughts in the comments. This is one debate that's just heating up.